Well, good afternoon, everyone. Because we have it streamed to the web, we get started right at the minute here. So thank you, everybody, for being here. We appreciate you coming to the first of our spring series for the Integrated Design Lab. I'm Ken Baker. I'm with Better Bricks Education and Training, and on behalf of the Integrated Design Lab in the University of Idaho in Bozeman, I'd like to welcome everyone here. I'd also like to thank our sponsors tonight, which are Northwestern Energy out of Montana and Idaho Power Company, and U.S. Green Building Council, Idaho. So once again, thank you all for being here. We have 4 sessions in this spring series. Tonight we're going to kick it off with design synergies and case studies. Basically, we're looking at that integrated design practice again, and Doug Boers is here to talk to us about it tonight. I'll introduce him a little better in just a minute, but Doug will be back with us next week because this integrated design is a 2-part session. Generally, we go for about an hour and a half. Tonight, we've kind of overbooked a room, so we're going to be done by probably about 5:30, and we'll have some time for questions after Doug's finished at 5:30. So we'll go from now till 5:30 with a little time for questions, and then they have an event in here at 6 o'clock. March 13th, I want to tell you about upcoming sessions. Doug will be back. Integrated design process. It's more specific about the process. Tonight will be an overview on integrated design, so glad you came for that. Next week we'll learn a little bit more about the actual process, and then on April 3rd we have a really good speaker here for net zero commercial buildings, what needs to change to get to net zero buildings. That's David Ajati, the principal with the White Group. Then April 10th, rethinking building commissioning. What has Guideline Zero got to do with it? And that's Walter Gronzik. He's a professional engineer from Ball State University. With that, I think we got the logistics out of the way. Help yourself to water and cookies over there. The restrooms are downstairs for those in the building. I'd like to introduce Doug Boers, who is our great speaker tonight. I've heard Doug on this topic and many others over the years, and appreciate you coming to Boise. Doug's from Seattle. He has his own company, Softmetrics. And with that, Doug, please take it away.
Thank you, Ken. You need to put your hand up if you can't hear me. This microphone is for our web visitors. I see a couple of faces that I recognize from 2 and 3 years ago. I'm curious right away how many architects we have this afternoon. Engineers? And others?
Property managers.
Oh, this is excellent. This is excellent. So 3 years ago I started speaking with NEA, and we were focusing on what we call the supply side. So we started by talking to architects and engineers. The idea was to get the message out that integrated design was an important thing and that it could be executed effectively within the structure that we already have for architects and engineers. Most recently, and especially this year, we're beginning to get the message out to property managers, to developers, to large building owners like Microsoft and the University of Washington, that the industry is ready for integrated design, and it's time now to tap them on the shoulder and say, go for it, do something good for me. So that's what today's conversation, as Ken mentioned, we'll talk primarily about the whys and the first level description of what we're interested in when we talk about integrated design. Next week I'll come back and talk a little bit more about the individual aspects of the process, the steps that one needs to go through to accomplish it. So if we don't hit all the details that you're interested in, by all means come back next Thursday. Northwest Energy Efficiency Alliance has helped to establish this presentation. In particular, Rethinking Design is a remodeling of the discussions that we were presenting 3 years ago and 2 years ago. The NEEA is supported in turn by Northwest utilities or electric utilities from a 4-state region around here. And I want to mention in the bottom bullet what the 2030 challenge is, which is a relationship with many different organizations, but including the AIA. The 2030 challenge is now looking forward for 22, 23 years from now and saying there is a point in our future when we can choose to be carbon neutral. And the context for that statement for the AIA is the building itself and the building's operation and the building's function. Carbon neutral does not necessarily mean energy neutral, but it means that we've established a relationship with other aspects of carbon use so that what we do use in our building plus what other things we do comes out on an even basis. For your information, not right now, but at the end of the session, there's a real short piece here called Carbon Neutral Talking Points. And in this paper, I've outlined all of the other things that one might consider in the context of carbon neutral other than just the building. Because the issue of carbon neutral goes into transportation, and it goes into the employees' activities, and it goes into your manufacturing processes and lots of other things. We're focusing today on the integrated design aspects for a building. But I needed to add that little bit of larger context because we referenced the 2030 challenge 2 or 3 times in this presentation, and then again next week a couple of times as a touchstone for one of the things we're responding to in the future. Okay, so what hasn't changed? We still need light and air, and people still work in spaces. And one of the things that I need to hold on to as a touchstone as I'm giving these conversations is a very straightforward aspect, which is that the effectiveness of our building spaces, especially in the business environment, but also in the scholastic environment, is valued more than everything we do in the building. I can give you 2 or 3 examples of that. A couple of the insurance companies now have taken their staff from older stock to newer stock, better ventilation, better lighting, increases in productivity, reductions in absenteeism. Numbers vary from 1.8% to 2.3%. Some of the extreme claims are 4.5%, 4.6%. Increases in overall productivity for a staff. Nominally, the building cost for a firm like an insurance company runs between 3 and 5%, the whole real estate cost of their bottom line. So if they can increase productivity in the range of 3 to 5%, they pay for the buildings. They don't pay for an incremental improvement in the air quality. They don't pay for better windows. They don't pay for a LEED certification, which all costs 2, 3, or 4%, or sometimes nothing extra. They don't pay for the increment. They pay for the whole building. So everything we do, as a touchstone, we have to come back to the notion that if we start to be really concerned about the 1 and 2 and 3 percentage points, that we had better be also very concerned that we're not undermining the functionality and the productivity of the building, because those are the baselines. So staying the same. And things change, and the technology, the materials, the tools, those kinds of things change. One of the most important aspects of this slide, the things that haven't changed are coming back into our minds. The things that haven't changed relate to how fast heat energy travels through an opening, in our case now glass. 1,000 years ago it wasn't glass. Through brick, through a certain level of insulation and sheetrock and weight on the ceiling. Those are physics, and the physics of heat travel in and out of buildings has not changed. And we've conveniently forgot about that physics in the last 50 or 60 years because it was very inexpensive to build an air conditioning system of whatever size it needed to be, throw it in the building, put energy to it, and we were scot-free, we were home. Okay. Recently, meaning ever since the 73 energy crisis, we've become more and more concerned about how we utilize energy. So what has changed is our reawakening to those old physics. Now, this is where I feel our attention needs to be from the standpoint of the design industry. It's not whether we're in new technologies or old technologies. It's not whether we have better systems that we can build for HVAC. It's how we wrap our minds around the energy that goes inside and outside of buildings and how it flows in and out and how that impacts people and functions. We have conveniently forgotten the energy aspect 50 years ago. And we didn't have to think about it for the 40 years since then, up until about 10 or 12 or 15 years ago. So what's changing in this decade is how we conceptualize that, notwithstanding all the rest of this. Now, one of the interesting aspects of that is that we now have some tools that we never had, which help us to conceptualize how this energy flow works. And the DOE 2.2 is one of those pieces of software that's been developed. The reason I mentioned that one in particular is because it now has a 20+ year history of mainframe computers modeling how energy flows and testing over and over again to see whether or not that energy model is valid. And now there's 6 or 8 other programs that depend on that software engine, if you will, to do the calculations, and we can trust a lot of the answers we get from that from the standpoint of how a building will interact with its environment. So another one of the differences, if we're mentally going to figure out what we're doing with this heat, is to rebuild the models that we have and use both in our minds and in computers to make that work better. Okay, this is my thesis for today. The Northwest Energy Efficiency Alliance has hired me to come out here and tell you that integrated design is something that we all should be doing. Just, we're done, we'll go home, that's it. That's what we should be doing. My thesis today is that integrated design, not integrated energy design, but integrated design has an application to a broad range of problems. Healthcare and making hospitals a better place. I just got done talking with Arlen Collins at Collins-Warman, and he was telling me about a group of hospitals that went in together and said to their team of architects, this is how we do business with patients in a building, in a hospital for 200 people. Fix it, change it, make it better. And the architects came up with a solution that turned the outside exam rooms and peripheral and emergency and all of this stuff into the core and centralized the testing aspects and the diagnostic aspects of the whole hospital for a 200-bed hospital. Put the patients back on the periphery, and now the equipment and the technicians stay put. And the patient travels to a diagnostic center, hits the 2 or 3 things he needs to do, back to their patient room. What happened? They use 40% fewer staff. The patient spends 80 minutes a day traveling instead of 240 minutes a day traveling. The quality of care has increased by a 2 to 3% margin from the standpoint of health and safety of the patients. That is, the diagnostics has improved. And they're using fewer technicians because the technicians are spending less time running around and more time in front of the equipment. It's because they took the old model and turned it inside out. They said the diagnostics and the equipment are what really matter here. This is the core of the process. Let's put it together. That was an integrated design process. That was that team getting into the hip pockets of the people in radiology and the people that actually had to execute the process of the hospital and turning the architecture inside out to make it reflect what was required. Okay? The integrated design process has a leading edge. And in my hospital example, this particular example is the leading instance of that kind of facility. But now the pattern sits there and we can think about it and copy it. In the energy arena, the integrated design process, I'm still working on my thesis here. A thesis statement is supposed to be what, 20 seconds long? The integrated design process has examples that it has left behind in the energy arena of things that we can do that make sense in terms of energy. Reducing equipment size, using a little bit more of the flywheel effect of a building, put a little mass in the building, use a tank to store cool water for an hour or 2, which allows you to reduce the size of your chiller. All of these kinds of ideas, we've already thought them up, we've modeled them 1,000 times, we've built 100 examples, we've got a way to go back and measure that they work or they don't work. Those were leftovers from this integrated design process that was out here. So my thesis is the integrated design process is absolutely critical to the way we change our notions of solutions. It's the way we change. It's the way we get better. And people can choose to be on that edge of change and improvement by participating in that process. And I don't care if you're designing a palm top or a building or a car. If you're on that edge of change, the team that gets together to design those things is closely related to one another, and they're going through a different kind of approach than a traditional approach where individuals have responsibility for certain aspects. That's the difference. That's the key. Now, one more thing to support my thesis. If this is the leading edge, then there's a trailing edge. Otherwise, my statement makes no sense. Well, the Advanced Building Institute now has a document out that you can find on the web. It is a list of some 30 activities or so, and some, I think it's 12 or 14 principles to follow. And if I hand that book out to my design team, and I say, okay, mechanical, you get this, electrical, you get this, architect, pay attention to these things, structural, you pay attention to these things, and people check off 3/4 of what's in the book. They say, okay, I've done these things. The net result is a building which is 20 to 30% better than a traditional building relative to where our energy codes are today. And those people don't have to meet at a special place for 2 days to do a charrette, to build an integrated design process, or particularly know really well what one or the other of them is doing. And that's because that collection of ideas has been tested, improved, and built and collected by the Advanced Buildings Institute. And now we have this leading group, which is the Integrated Design Group, and this following group, which is, it looks an awful lot like a textbook or a prescription. So to complete my thesis statement, what I'm saying today is the integrated design process is for pushing us further and further along the energy bar to make ourselves better and better in the future. You don't need it to do well. The question is this well enough or not? I don't know. I don't know the answer to that yet. My gut tells me it's not well enough, and this is why. A few years ago, I was giving an energy presentation. This was probably 7 years ago now. And a gentleman from Amsterdam stood up after I had gone through my 10-minute spiel, and he said, I left Amsterdam a couple weeks ago, and I've been looking around Seattle. And I have to tell you guys something. You think you're proud of the last few energy efficient buildings that you've done. The very worst building I left behind in Amsterdam is better than the very best building I've seen in Seattle in 2 weeks. By a 40 or 50% margin. From what I understand, what we've accomplished so far, starting here, if our target is even where Europe was a few years ago, we had 2/3 of the way to go. They were running 30 to 40% of our energy loads. If we've cut 30% off of our traditional codes, and we can do that easily now with a new building, we're halfway. So yeah, I think integrated design, good idea. Keep it up. Okay, so I'm going to pass this out for the folks that are, it's just one sheet. If you pass it around a little bit, there might be enough for everyone, I'm not sure. The folks that are on the website, do we have there is a document copy of this that's ready to go. It's basically a bullet points, a talking points list for Banner Bank, and this is a 2-minute effort, if you will, to get people in the audience involved here a little bit. The Banner Bank is right here, 180,000 square feet, nominal energy cost of $1.50, an energy savings of about $135,000 a year. Okay, so I'm going to do a little bit of math that the folks that are property managers might be able to understand this math even better than I do. In order to build a building and run it, you have to borrow money. And if you don't borrow money, you're using your own, and you would like your own money to create money also. So whether you borrow money or not, you still have a value of capital that we work against toward the future. Okay? In this particular example, they're taking a cap rate of 8%. So they either have to borrow or they want their own capital to generate about 8%. So if I invest $1 million, then I would like to get 80,000 back from that. But you can figure that equation upside down, which is if I can save $80,000 a year, and that savings is associated with the physical structure of the building, then in theory, if the building does its functions correctly and houses the same number of people, then the building is worth $1 million more than it was before. And what they're saying here is if I can take $135,000 a year at a cap rate of 8% and tip that equation upside down, that now my building is worth $1,687,000 more than it was right now on the resale value for the market value right today, which is about $9.37 a square foot. Now the claim that's being made for this bank building is that through the integrated design process we saved a bunch of money and a bunch of energy at no increase in the first cost of the building. So by putting the design team together, getting them to sweat a little harder, we came back with added value right out of the gate at no upfront cost. That's the claim. Okay, so what I'd like to do, since we have but an hour, we don't really have an hour and a half, so we don't want this exercise to go on for too long, is to take this list here, and the one that I'm most interested in is which measures are state of the shelf right now. And really what I'm interested in is what's in your heads is state of the shelf, because that's what matters, what's going on in Boise, and I don't know that right now. So the handout that I gave you has a list of talking points. It's basically the things that were done in the Banner Bank to make the Banner Bank a more effective place to live and work. It's not a residence. Which of those measures are state of the shelf? Does anyone want to respond to that right now? I haven't had a long time to look at those things. Everything is state of the shelf. Okay, so
They didn't create any new signs or anything fancy. They just did what's available.
okay. Okay. So raised floors, they're state of the shelf from the standpoint that they've been tested in a few hundred buildings. We've seen them around the nation, but you wouldn't consider them to be necessarily new to Boise. Yeah, okay. Okay, so there's a test for you. So here's a challenge, and this goes back to a story that when I was a youngster, my family was driving to Alaska for a vacation, and I was a talkative youngster. My father was a little bit tired, and we would driven across Canada, and we were on our way to Alaska, and so he'd probably listened to me for 40 hours during the previous 3 or 4 days, and there was a sign that said Alaska, 13 miles. So he said, I'll give you $0.25 if you can be quiet till we get to Alaska. So until I saw the sign, and before we crossed the line, I spoke out, there's Alaska, and he said, oh, you almost made it. But I'll give you the $0.25 anyway, because you were really good about that. But now I know you can do it if you want to. Banner Bank is sitting right here. And so what you're saying, this stuff is all state of the shelf. So now I know you can do it if you want to. Now if the real estate people are saying, you know that 8% thing where we flip and where it's worth 1.6 million, and if that calculation is valid, now not only can you do it if you want to, but every building owner wants you to, and it's the new standard. We're there. And if you're going to compete with anybody to do better, then we're back to our integrated design story, because you've got other things to try to find out to accomplish. But that's our new standard. We all need to learn about it now. Is that fair or is that crazy? Anybody want to push back on that?
Are you back to searching for new things in order to make it better? Or are you back to the book of all these things that have been proven? Let's add some more to it.
I'm going to go both ways. Oh, okay. Are we pushing, I'm going to rephrase slightly. You can throw something at me if I'm wrong. Are we pushing the edge of improving an individual building by integrated design, or are we trying to improve the whole lot and add more items in our menu of items by doing integrated design? Okay, certainly both, but here's the game. Architects and engineering teams have to compete. If they're going to be the best now, 3 years ago I couldn't say this, but if they're going to be the best now, they have to work together better than they used to work together, flat out, for every building individually. As that happens, people like NEEA and the Integrated Design Lab are going to try desperately to save these ideas up so that we can share them around so that not everybody has to reinvent them over and over. Now, having said that, there's a trick here. The Advanced Building Institute is very careful to say in the front of their book that not all of these ideas work everywhere. And so you still need people to sit down and talk through them and decide which ones are going to be the right ones to dump into the bucket in Boise, which ones are going to be dumped into the bucket in Salem, Oregon, which ones belong in Seattle. The ground sink tempering the energy use through a heat pump type of a deal, it's no big winner in Seattle. Wins a little, but out here, it's a big winner. Why? Because you can have a really hot day and a really cold night at the same time in spring. In Seattle, if it varies more than 20 degrees between the night and the daytime, we've had weird weather because it's humid. So different places, different advantages. We still have to have intelligent people applying these things in the right way, which is the part of the question that you didn't ask. How do we make sure that we don't build this menu and then misuse it? We'd hate to do that. We're making a claim that the integrated approach involves more effort up front here. That's easy to make. We're also making a claim that if you do this up front here and establish your requirements and make some choices and get people heading in the right direction, that during the conventional aspects of construction, and especially construction documents right here, that the design team spends less time chasing their tails, less time doing the detailed things twice. And here's an example for that. If I'm a mechanical engineer and if I'm working for a university that requires that I size my ductwork as part of my deliverable, then I've drawn all this beautiful two-line work on my drawing. And if at that point I change my mind about what the criteria are for the ductwork, I redraw the whole thing. I'm back to scratch zero and start over. Or maybe I redraw 2/3 of it. If instead I've made a very solid decision up here about how much air I'm moving and why I'm moving it and what my cooling driver is, I'm very less likely to have to draw my ductwork twice. And that's where the argument comes in that the design team will save some effort later on if they've made sound decisions early on and spent their time together. Now, if you take a really careful look at that, there's a little more area under the curve that we've added and a little less area under the curve that we've saved. Okay? And this is, we have to sell this to all of our property managers and land developers. And here we go. Get down on my knee. We've been saying, and I've been saying since 1980, which was the first year that I practiced engineering, that if you could just give me an extra % or 2, I could save you 6 or 8% in my system just by spending a little extra time thinking about it. And that's a generality that goes across all systems. You know, how could I better locate my electrical room? Can I do a calculation that will optimize the best place for my electrical room? What if I use 2 rooms instead of 1? What if I use 3 communication centers instead of 2? We don't have time in this industry to check all of those options as a part of our design process, because we compete with one another, and on a national level, we've decided that somewhere in the 3 to 5 to 7% range, depending on whether you're in Class B, Class A, or healthcare, that's what you get for the fee. And if that's what you get for the fee, we're going to try to make some really good decisions and then draw the thing. Okay? You don't want us to draw the thing. We've got a lot of people who would really rather think about the thing. But they need that extra percent. They need to go from 5 to 6%. My hunch is, and this is a little bit of salesmanship, but not much. My hunch is, if you gave people, instead of 6%, 9, instead of 10, 15, as building owners and developers, you would always win. Because you just get that much more value back. They're leveraging 10 to 1 odds. If you can spend a little more time thinking about it, you can optimize a little bit from the monetary side and pay for your time. It's never failed for me. Okay, so here's the game that we're trying to sell. The question is, do you believe it? And not all of my owners do. Right? So here's a list of things that are suggested. I'm going to let you read through some of them as I yak. But the last one, the commissioning and post-occupancy assessment, is now where our attention is. And so given that I have an hour instead of an hour and a half, which is okay with me, I'm going to skip the other points and then concentrate on that commissioning piece. Because when you talk about integrated design and what we've been doing for the last 10 years, and then talking about for 3, if you talk to people now, their knife edge is on the commissioning piece, and then the lead standard for existing buildings is now on the measurement piece, is where the knife edge is. Why is that? Because buildings that were built 4 and 5 years ago, in some cases, are operating just as poorly as their neighbors that were built by standard practices, because things have been allowed to go downhill, settings have been allowed to slip, heating systems are humidifying and dehumidifying at the same time. I mean, dumb things happen. And unless somebody is watching the electric bill and gets upset about it when the electric bill goes up, those little problems with the mechanical system are rarely captured, or at least they're only captured slowly, once a year, once every 2 years. We're doing a little adjustment. Oh man, I should have told you that was out of adjustment. How long has that been out of adjustment? How many months have I paid extra bills? So the lead existing building qualification set now includes, let's measure some of these things. Let's track them. Let's put them on a computer month to month. Let's compare this May with last May. And let's try to justify the changes in our mind or go fix it. One or the other. I've got a building I'm working on right now that we have not resolved the issue on yet. That we have, it's a phone switch. It's all it is in that building. There aren't even any people in there. It's a phone switch. And they told me that they have 10 tons of cooling units in there that last summer they claim were running wide open and there's no more capacity. So I went in and felt the phone switches and looked up the nameplate rating and looked at the meter readings, and I checked a site in Germany that has the same phone switch in it from Northern Telecom just to see if I was out of my mind. It's 12.5 kilowatts of phone switch in there. 12.5 kilowatts should take 1.5 or maybe 2 tons on a hot day to cool it. And they're telling me 10 tons is running wide open to keep this building cool. And I've already said out loud on several conference calls, the system is broken. Go fix it. They want me to add some phone switch in there. So I said, I'm going to add another 8 kilowatts of load. I need another 2 tons of cooling, or 1.5, whatever it is. And they said, oh, the system won't take it. It's full up. And I said, fix the system, and then we'll put the phone switch in. And but that's the story. The numbers do not work out. But nobody is measuring what's actually happening in that building, except the technician knows all 4 units are running wide open in the summertime. So they can't have any more capacity. Okay? This is where the knife edge is now, post-occupancy assessment. Okay, I'm going to glide past this one. Here's our next group discussion. We're not going to bother to make this a big event, but here's our next group discussion. A show of hands, and there's the question, why is integrated design not being used more often? Now, I have to be careful here because I'm a visitor to Boise, and I don't know, maybe all the architectural firms here are already into this gig. And I know that at least half of the firms in Seattle, and maybe more, insist that they follow integrated design and that they've been establishing the requirements and passing that on to their consultants for decades now. So what's new about this? But in Boise, why not, if it's not being done? Ideas? Perceptions from building management? Why not? Why not?
Expensive.
It's expensive. And where does the expense lie?
Probably in construction, material, and designing.
Okay, so we've got design costs, which could increase. And we kind of talked about that. I'm obviously in favor of increasing design costs, but that's okay. And we've got construction material increases. And I didn't hear you say it, but perhaps if you ask a contractor to do something different, at least he's going to be a little careful how he bids it the first time until he learns how to do it. So you might pay a little extra for his learning curve. Is that fair?
Yeah.
Okay. What else? Time. That's a good one, and I hadn't even thought of that ahead of time. So what could happen is I could increase the length of time that I have to design and construct something. We went through, and that's a very good one, we went through a lead charrette process for one of the Microsoft projects that I worked on years ago, middle 90s. The primary criterion that they had handed us was very simple. We signed the lease in February, whatever year that was. We're going to move in to our first building April 1st the following year. 250,000 square feet for that building. And it was one of 5. And it was on a campus. And we had to build a roadway and 2 big parking garages. They're going to move in 14 months after they signed the ground deal. That was the only criteria from the standpoint of, thinking about it from a design standpoint in the middle 90s. We used to get 14 months to design buildings that were 250,000 square feet. So crisis. Well, you couldn't add to that crisis to have to do something about energy. Well, they said, yeah, you have to do the lead charrette. So we fit it in. And we did get them into the building on time. But a lot of people worked long hours and weekends to make that happen. So it wasn't easy. But that's a crisis. Time. Anything else? Okay.
Changing status quo, fear of roles changing, power struggles, that sort of thing?
Fear of the new. Okay. There's a group called, now I can't remember whether Collaborative for or something about, but it has to do with the way that conversations occur in business. And it's a European group that's associated with one of the universities over there. Complexity in Management. The Complexity in Management Center is what I'm trying to think of. They've come up with a thesis that every conversation we have is about 2 things. We need to share information. Fair enough? Easy. The second thing every conversation is about is your power relationship. Interesting story. It's easier for me to stand up here in front of you and talk on than it is particularly if I were to meet with you afterwards and me talk to 2 of you and one of you kind of push back on some of what I'm saying, and I'm not quite as aggressive in that because I've got the power advantage standing up here. Okay, the conversation has already been set, so I can ignore that and just talk about stuff, about the information. But every time humans interact, it's partly about that power relationship. And if you take an individual into a room for a charrette and you say, we're going to talk about all of these ideas as if they're equal ideas and we're going to bat them around for a couple of weeks and then we're going to pick the good ideas, it changes the power relationship among that group of people. The architect is no longer handling the mechanical and electrical people as raw subs. They are at least on par for a while. And if we're doing this in an ideal way, we have the owner in the room. Even ideas. We're going to talk about these ideas. I've been in several cases where that's worked very well because the owner knew how to do that game. I've also been in 2 cases over the last 12 years where we've gotten in the room, we've put the ideas out, the owner's walked into the room and he says, that one, that one, that one, and that one are stupid. Kick them out. And those guys can go home anyway. We really don't need him in the meeting, you know. The charrette was done. The value that we could have produced for the owner in that circumstance was done in that 1 minute. It's gone. Nobody was going to speak out again about any brilliant idea. Fewer than a power relationship. So those are very good. Turner Construction asked around, and they came up with answers to the same question that I just posed you. And this builds a hierarchy, because my guess is all of the other things we talked about, including time and power relationships, are also in there. But it's money, and it's not knowing why you're going to do it, are the big items. The big items. What's it going to buy me anyway? You know, what good does it do me to save 20% on my energy cost? So we talked about that a little bit with Banner Bank, right? So is it actually additional construction cost? These studies on here all say that the increase is slight or small. The Corps of Engineers did a study which involved 300 buildings. Some of those buildings were Corps of Engineer buildings, and some of those were other buildings they went to study. And they tracked this group over a 15-year span. Now, LEED didn't exist necessarily back that far. So what they were looking at was, what does it cost me if I tell the architects and engineers to do a better energy building for me? Don't waste so much energy. And they tracked that cost. And it started out at 6 or 8% high 15 years ago. But there are very few design and construction teams now that allow themselves any additional cost for what we're trying to accomplish now. It's just one part of the goal set now. It's not supposed to cost anymore. And oh, by the way, some other people have done it without costing anymore. So we go back to that example we were talking about with the bank. That's the standard, right? Now that's one side. Does it actually cost more or not? Okay, maybe we should allow the fear that it costs more, or allow that we're going to pay our group a % extra up front, or 2% for the design effort. Maybe we'll invest a little more time in it, maybe not. Okay, energy prices have changed in the last 3 or 4 years, radically up, then a little bit down, radically up, then a little bit down. I did a study for the Port of Seattle that would look at connecting the cargo ships to an electric plug. The electric plug for a cargo ship averages $1.7 million a piece. It's a big deal because I have to dig over the dock and then I have to build this thing, and $1.7 million. So our first estimate was, okay, the day we were doing this work, the cost of the junk that they burn in those ships was running about $210 a ton. And in Seattle, it cost me about $300 of electricity to avoid burning 1 ton of this muck. Okay? It's never going to work. It cost me more for the electricity, and then it cost me $1.7 million for the plug. But this muck has been very volatile in pricing. And yesterday, when I looked on the web, it was $580 a ton for this muck. And in Seattle, our electricity prices have gone down ever so slightly because we've retired some of the pain that we felt when California was going through its agony. And now it's about $280 of electricity to avoid burning 1 ton of this muck. Now it's starting to think like, well, I'm going to get $4,000, $5,000, $6,000 a day leverage advantage, payback, if I had this plug on the dock. It's not because the construction cost of the plug has changed, it's because the fuel price is doing this. And depending on which date, well, that kind of volatility business managers tend not to like. They tend not like to get a bill for an extra $135,000 at the end of the year and say, well, electricity's gone up. Natural gas has gone up. So we're going to reduce that. We're going to reduce the raw expense goes down as we did in the Banner Bank piece. And then we're going to get some of the other advantages which are a little bit less obvious in terms of better daylighting, better health, better accountability for the neighborhood, that kind of thing, with these energy savings. So we do have reasons to do it. And the results are quantifiable and advantageous. But now I'm going to go back to the first thing that I talked about, which is the touchstone. And here we have to be careful because the architects and engineers have to realize that I can obtain this touchstone without also being energy efficient. But often, because we're being so careful about our integrated design process in order to attain energy efficiency, we get some other advantages. And this is an example, is the daylighting issue. Okay? CHIPS in California studied over 1,000 classrooms over a period of 6 years. Okay, so this is like 30,000 kids. They followed through 3 school districts through grades 1 through 5. So it's a statistical sample that's fairly significant. And they correlated the quality of lighting in the classroom with lots of other things. Okay? Now, lighting in the classroom has got some real narrow variations. You know, if you can see out and the sun can come in and you know what time of day it is, that's pretty cool. And so giving you better daylighting technically above and beyond that pretty cool doesn't really cause a whole lot of difference. But measurably, going from a classroom with paper on the windows because it was facing a disturbance like a park or a playground where the teacher had put paper on the windows, from that baseline, which is the worst, to the best baseline, which is a facility that was designed intentionally for daylighting, and the criteria is for that, the whole room, the lighting can be turned off all day long because enough daylighting has been brought into the room to make that much difference. I can do all of my functions with all daylight, no lighting put in there. So that's the best. Best to worst. Classroom performance against a sample set of 30,000 children over 6 years, 20% improvement. The 4th graders were operating like 5th graders for the ones who had been in the best lighting circumstance versus the worst lighting circumstance. The teachers union was upset about this report because it gave the most experienced teachers and the less experienced teachers a difference of quality of what their impact was. It was a 5 to 7% improvement. But the lighting was making the students' difference by 20%. Best teachers, the most experienced teachers, to the newest teachers, made less difference for the kids than the daylighting. Okay, ouch. But what does that say about architecture? It says if we walk away from a building and somebody has to tape paper over the window in order to make their classroom work, we have made a horrid mistake. Okay? So one of the benefits we talk about here, without having the 100% certainty of connection, but with having a clue that it could be huge, is that we can improve the case for productivity and learning while we do this other part of this integrated design effort, and then save some energy. Okay? If that's true, and if it doesn't cost much, then we're back to, okay, integrated design is back in again, let's do it. Just no choice, no question, just do it. Just do it. So what's the difference? The difference is that we're trying to take pieces of things now and put them together so they work in something that's greater than the sum of its parts. Okay? And from an energy perspective, I'm not going to go into the other aspects of how buildings operate. I'm just going to talk about the energy perspective for a minute. We have a mental model where we have a building element. Inside that building element are these pieces. There's where the building is, Boise, Idaho. There's what the building's used for. In the case of the office building down the street, it's an office function. There's the site and building design. What are my limits? Where are the street edges? What can't I do? Okay. And that building envelope and that series of decisions you create and how long people are in the building and what their comfort zones are, et cetera, all add into a pool of things that result in a series of loads. And those loads mean I need either to add energy or take energy out, which is really heat load, of this building. And I need to do it with my systems. So in this box, this systems means my mechanical and electrical systems. Mostly mechanical. You know, my wiring isn't going to change the energy use too much, but the fan motors will. Okay? So there's our mental map. If you take the work at the University of Oregon, they try to repicture that mental map where they're giving you clues about what you can do to design the building now. If occupancy, program, and schedule have something to do with use, that's going to point to doing certain things for the building. And there's an example for this one in Toronto at one of the universities. The mechanical engineer it was Keene at that time, took a building that was programmed with classrooms on the bottom, a commons area on the second floor, and professors' offices on the third floor. Big box. Keene Engineering said, if I take the professors' offices off the top floor and I put them in a box caught in the north edge of the building, and it's more like a cube than a flat piece on the top floor, I take the two largest classrooms, I put them on the south corner, I took the common area and put it back in the middle next to the office area. I can now manage this building so that I have 3 different zones associated with it. I can let the meeting space for the kids float pretty much. I don't care if it's 65 degrees or 75 or 78 degrees in there. I don't care too much. I'll bound it. It's in Toronto. It's not going to be 0 degrees, but we're going to hold it there. We've got this nice cube, which is the almost ideal insulated shape for the professors. That's their offices. And I've got these 2 classrooms now that several months out of the year are on the corners, and I can open the windows. Now they're facing away from each other, so they're not interfering with one another, and I can get natural ventilation through the corners of these classrooms. And then, oh, by the way, the covering on the classrooms now became roof structure, which is lighter than the structure underneath the second floor, so I saved a little money on my wide span where the classrooms were. So they weren't just toying with this. They probably thought of 50 different options before they picked this one. But they turned the building inside out. They talked about the occupancy program and schedule, and they found how to reduce the energy of that building by a significant amount with that reorganization. They won 40% in the energy load of the building before they got started with the mechanical system. Okay? I'm going to skip that and we'll go on to this. So here's our conventional piece that we see now. Traditional load that's being dealt with a traditional system. And I approach the model mentally by saying, okay, what if I get the very best chiller I can? What if I get the most efficient fans I can? And what if I put a heat exchanger in? I'm going to spend more money for this stuff. Okay, which is the question. Where do I spend more money? I'm going to spend more money for this stuff, but I'm going to save energy. So here's a case where I look at the systems, spend more money, save energy. So the question is, how long does it take me to pay back for that? Okay. Here's a system. Now I take this conventional system and I operate on these things and reorganize the building itself so that I cut the loads in the building. The example I gave you for the college was 40%. This one says 50% for purposes of the visual. So my loads are 50% smaller. If I address this with a traditional quality system, I only need half as much system. Half as much chiller, half as much fan energy, maybe the same ductwork. So it doesn't cost half as much, but it costs 40% less, and I use less energy. So I've gotten the same result here by addressing the building rather than the other. I'll go back one. It's 50% energy, 50% energy. Now what if I put the whole team together and I say, we're going to take this optimized loads thing we looked at the first time in the slide before, we're going to optimize the systems approach now, which is we've pressed the building loads down and we've pressed the mechanical system down. Now the energy use is 1/4 of the original footprint. Now it looks more like the fellow from Amsterdam was yelling at me in my energy presentation and claiming that his buildings were all more. Now we match him now with this. Okay, how much does that cost? Well, this is the kind of the game that we're playing with our heads, with our chart here. If we fight to reduce energy use by 10 or 15 or 20%, we end up somewhere on this bar, we end up spending some extra money and trying to trade that off against the future. If we can reduce the loads of the building, at some point or another, we reduce the equipment that we need. We reach a point where I don't need a 10-ton system, I can use an 8-ton system. There's sort of a magic number there, or from 10 to 6, and I drop the cost. Now that gives me room to spend a little bit more on other efficiencies, and in theory, there's some place in here where I come back up to this, no added cost for the owner, but I have a net result of less energy use. Okay? So the Corps of Engineers and these other folks that are studying buildings didn't know to look for, and we don't have a way to go back and correlate which ones of the buildings were where on this curve. At some point or another, we can eliminate the equipment and spend our money elsewhere. Vancouver, British Columbia Public Library is an example of this. Who's already heard this example? Ken says yes, no one else? Okay. Vancouver Public Library, internal structure is concrete with a raised floor, and when they need cooling in the summer, this is a cooling example, they don't need it very often, but when they do, they pre-cool that piece of concrete at night. The mechanical engineer was afraid. We talked about fear of change, right? The mechanical engineer was afraid, so he put in a 300-ton cooler unit just in case cooling that floor at night didn't always take care of the cooling load that was required. Well, it turns out that, at least as of the last time I checked, which was last fall, that chiller has never been turned on. Was not required. Because the solution for the building with a raised floor and pre-cooling the slab was good enough that not the heating equipment, but the cooling equipment, the chiller, could be eliminated and cause this dip. Okay? That's what we're looking for with integrated design. We get back to the 2030 challenge and talked about two things, getting to 50% reduction in energy by when? 2010, and getting to even or zero carbon added by 2030. What this challenge by 2010 means is that anything you're doing right now, you're in the game right now. So that's the curiosity about that time. I'm going to skip past this one, and we're just going to go right back to here. The interesting piece on this, and you might want to write this one down, I talked about the advancedbuildings.net and the New Buildings Institute. That's where that document is that has the prescriptive things that get you the first step of the way, then get you to that 30%, 20, 30% energy savings I was talking about without necessarily changing your relationship in terms of the integrated design piece. Okay, I'm going to guess that several things are happening here. We were charged with fitting into 60 minutes from the standpoint of presentation. We have a caterer who's expected to come in about 15 minutes. to set up for an open house. So we've done our 60-minute trick. We're right on target. And we've left time for questions. And I'm curious if we could turn the lights back on, maybe we'd see a little better for the question part. And I appreciate this glowing thing back here, but does anybody need that left up yet for a minute? The advanced building thing? So questions?
So what is the catalyst for getting integrated design started?
The building owners. No, I say that a little bit facetiously. The competition in Seattle now at the architectural level is such that no one that I know of is not thinking about it on every project. It is also the case that at least for 40% or so of what's getting built, there still isn't support on the developer side. The developers haven't bought the story yet. That's why the attention of NEA is shifting from the architects to the developers. I now go talk to architects and they say, yes, we would love to do an integrated design process, but, and there's two things that they answer. One of them is, the developer that's hiring me isn't asking me to do that. Now, the Corps of Engineers is asking you to do that for the Army. The University of Washington is asking you to do that. The City of Seattle is asking you. The State of Washington is asking you, but not all the developers are asking you. And the second pushback I get is the architect will say, you know, the mechanical and electrical people that I work with, if I invite them to an early meeting, they don't know how to make recommendations and decisions without any information. They can't really operate with a cloud. And so there are still some people that haven't had a chance to practice this early decision process, and they don't know how to do it. And I have to give them, you know, okay, fine, either find another mechanical engineer or hire a specialty lead consultant to come in and sit down with them and help them through it the first time. You know, those are both possibilities. But those are the 2 points of resistance that I hear about. Did that answer the question? Anything else?
don't understand the comment by the architect that the developer hasn't asked me to do that. The architect and the design team wouldn't ask the developer, how should I go about designing this? What things should I do? They wouldn't give up that part of their practice. Why would they give up this part of their practice?
So, okay, the question or comment comes back, why should we wait for the developers to tell us to do this? Because it looks so much like the right thing to do right now, based on the evidence that we have. Shouldn't it be part of the practice? I agree with you from a philosophical standpoint. It should be part of the practice right now. But we wouldn't introduce. I did a project for, it wasn't Vireo, there's another group that's doing some healthcare work with healthcare records. And we put in a wireless network for them. Well, there's a HIPAA requirement that requires that you keep everybody's healthcare record private. So a wireless network in a healthcare environment means that I have to know everything there is to know about security on a wireless network so nobody can tap into it. So even though it was the right thing to do in the building they were moving into and it was the right solution, it was imposing on them some risk. And as a consultant, I felt it was appropriate to let them know what that risk was. Their IT guy was going to have to learn how to secure the system, and we would have to watch that level of security from day one, just like you have to babysit a building to get the best energy performance out. Well, if I go to one of the established developers in Seattle that produces 200 units of housing every year, and I flip what his house looks like. So when he walks in, he no longer has the traditional furnace, but he has a heat pump and a ground loop. He doesn't know how to take care of it. So I can't quite get away with doing that without inviting him into the conversation. That's where I'm concerned as a consultant, to not push him too far. But I agree with you from the other side of the coin, which is We should put that on the table for them. You know, the best thing you can do for these 200 units of housing is this.
Well, I would buy the argument if that developer actually took care of that equipment.
Yeah, yeah, yeah. That's fair. You've got me.
Other questions for Doug on the integrated design process tonight?
How do you make a building that's flexible? I mean, you mentioned the class, the school building. What if 5 years from now they go, hey, we need that for offices? So you've designed first off this thing, especially built with offices in one corner, big wide area in another, classrooms in another, and they come in and say, sorry, we need it for offices now. What happens now?
Okay, so the question is, at what point do you lose flexibility because you've turned something inside out functionally and made it more specialized from an energy standpoint? The first aspect that I would push back on your question is that if I build a traditional classroom facility that's just classrooms, and we still make some of those on college universities, we have the same question that's left over. If I try to take a traditional classroom, 30 by 30 bay, and move into it as an office structure, it's not going to be quite as comfortable. And if I built a classroom structure that seats groups of 90 to 120, I've probably raked the floors. So I have a elevation change for my seating. That's not going to work as office space either. So we give up some of the flexibility you're asking about, we give up anyway, whether we've done it correctly energy-wise or not, we've still given up the flexibility functionally. Coming back the other way, there are cases where we've moved into and re-inhabited office buildings that have had raised floors, which are a big winner from an HVAC standpoint, where re-inhabiting that space has been easier from the standpoint of making more meeting rooms, a larger IT room or data center, those kinds of transitions, which actually worked out as much to an advantage as a disadvantage in terms of re-inhabiting the building. So the long-range answer to your question is to take flexibility as an object and make it a goal and treat that as one of the goals on the plate with all these other things when you do the integrated design, and test ideas against flexibility as well as energy as well as function, which I think is, we were asked to do that a couple times. One of the first raised floor projects I put in was the Department of Environment for the state of Washington, or Ecology, I think it was, for the state of Washington. And we ended up with a low raised floor system so that we could change the electrical and communications quickly for that kind of flexibility. Was that helpful?
Well, it was. I mean, the things that we face as property managers mostly is our buildings are existing. So, and they're constantly, and people are moving out, moving in, you know, so, and there's various configurations that the new tenant wants that have to be destroyed, you know, the old ones destroyed, new ones put in, so, you know, and my venture to say is that integrated design is, the amount of new buildings going up is a fraction of what is existing that needs to be dealt with, you know, all the time.
So part of encompassing that answer, when you talk about it in terms of old stock that's being re-inhabited all the time, goes back to a sales pitch that sounds more like one of the furniture manufacturers than architecture. But if you throw away enough sheetrock and enough material that has had to be built and then torn out because the office wasn't the right size, then at some point you get to the place where you could have paid for a movable partition system, which mounts and demounts on a raised floor so that the electrical and all that sort of thing gets reutilized, even if somebody wants an extra 4 feet in the corner office. You just pick it up and move it over and put it down. It's not quite that simple. There's quite a bit of labor involved for reshuffling these things, but you don't throw away the material load, which from an environmental standpoint is not good. So you win the community responsibility piece and you are more flexible. The downside is, at least historically, those have been more expensive at the start point. The question is, how many times do you have to move it until it's no longer more expensive? The answer these days is twice. And I don't know, you know, it's getting pretty good. If you have to accommodate 2 users and they both are willing to use the same removable, mountable partitions, you come out ahead.
Well, I'd like to thank Doug. Can we all give Doug a hand here? Thank him for.
Thank you.
Please come back next week, and Doug's going to get into more of the details, the hands-on parts of integrated design. Appreciate your willingness to come back to this audience. Appreciate all you coming tonight, and on behalf of the Integrated Design Labs in Idaho and Montana, thank you for being here, and hope to see you next week.